There are basically two ways in which the temperature of an air parcel can be changed. So-called diabatic processes involve direct energy exchanges. An example is the heating or cooling of the air as it moves across a hot or cold surface. So-called adiabatic processes do not involve net energy exchange. Heating or cooling is achieved by compression or expansion of the air. Here is how adiabatic processes work. Imagine you have air molecules flying around in a chamber. High temperature means that the molecules have high kinetic energy. They're flying very fast. If I compress the air, then the air molecules will start flying faster, which means that the air is getting warmer. When I expand the air again, the air molecules are flying at a slower speed, or in other words, the air cools down. That is an adiabatic process. That begs the question how air in nature is compressed or expanded. Remember that air pressure decreases with altitude. So if an air parcel rises for whatever reason, it will get into a region of lower air pressure. As a result, it will expand and cool. If we force an air parcel to rise, it will expand and cool. If we force an air parcel to sink, it will contract and warm. As long as there is no condensation involved, the temperature of a rising air parcel decreases at a fixed rate. This rate is called the dry adiabatic lapse rate. It is 10 degrees Celsius per 1000 meters. That means if your surface air temperature happens to be 32 degrees Celsius and you force the air to rise up to 1000 meters, the temperature will be 22 degrees Celsius. You force it up to 2000 meters, it will cool down another 10 degrees, so its temperature is 12 degrees, and so on. The opposite happens when you force it to come down. It will increase its temperature again at 10 degrees per 1000 meters. If an air parcel is lifted high enough, it will eventually get so cold that it cannot hold the water vapor any longer. This is the height at which saturation occurs. It is also called the lifting condensation level, because further lifting will cause condensation. Condensation means that water vapor gets from the gaseous into the liquid states. We see the formation of clouds. In this example, the dew point temperature, which as you know depends on the water vapor content of the air, is 2 degrees Celsius. At 3000 meters, the air reaches its dew point, 2 degrees Celsius, so any further lifting will cause further condensation and formation of the cloud. The process of condensation releases energy. Therefore, the rate at which the air temperature decreases from the lifting condensation level upward will be less. The air parcel still expands, it still cools down, but not so much anymore due to the fact that energy is released through condensation. Beyond the lifting condensation level, air parcels cool at the moist adiabatic lapse rate, which is approximately 5 degrees Celsius per 1000 meters. It is also called saturated or wet adiabatic lapse rate. The real value can be between 4 and 9 degrees Celsius per 1000 meters, depending on the amount of water vapor that condenses during the lifting. Remember that the dry and wet adiabatic lapse rates are values for the temperature decrease of a lifted air parcel. These are not values for temperature decrease with altitude that can be measured by taking temperature readings at different altitudes. In Chapter 2 we have already talked about the fact that the temperature within the troposphere decreases with altitude. This decrease of temperature with altitude is expressed by the so-called environmental lapse rate, ELR, which is also named ambient lapse rate. Similar to the other lapse rates, It's expressed in temperature difference per 1000 meter altitude difference. The environmental lapse rate varies with time and place. It depends strongly on surface temperatures. Solar radiation causes surface heating during the day. This generally leads to high temperatures near the surface and consequently a high environmental lapse rate in the lower atmosphere. Terrestrial radiation causes surface cooling during the night, which typically results in a small environmental lapse rate. When the near-surface air is even colder than the upper air, we call this a temperature inversion. The horizontal transport of air, called advection, is another factor that influences the environmental lapse rate. Advection of cold or warm air at different levels, for example due to varying wind direction with altitude, causes changes in the environmental lapse rate. I mentioned earlier that adiabatic cooling occurs when air expands because it is lifted. Four principal mechanisms can initiate the lifting of an air parcel: orographic lifting, frontal lifting, convergence, and convection. Orographic uplift occurs when mountains act as barriers to the flow of air. Air ascends the mountain slope, causes adiabatic cooling. This often generates clouds. Many of the world's rainiest places are located on windward mountain slopes. When air reaches the leeward side of the mountain, much of the moisture has been lost. Air descends, warms adiabatically, and condensation and precipitation are not likely. The results are rain-shadow deserts, such as the Great Basin Desert in the western United States and the Patagonia Desert in Argentina. The rising air on the windward side of the mountain range cools first dry adiabatically and later wet adiabatically. The sinking air on the leeward side of the mountain range warms only dry adiabatically. The results are warm downslope winds on the leeward side, such as the Chinook winds in the Rocky Mountains or the Föhn winds in the Alps. A front is a line where cold and warm air masses collide. This causes the lifting of warm air, which is called frontal lifting. A low-pressure center, also called a cyclone, always causes air to converge. Horizontal convergence always causes air to rise. Free convection occurs when air is lifted as the result of heating near the surface. This is localized over fairly limited areas and can result in localized thunder showers. So what makes air rise? In nature, there are two forces working on an air parcel. Gravitational force tries to pull it down to the Earth's surface. Buoyancy force tries to pull it upward. Buoyancy force is simply the result of the fact that we have higher air pressure near the ground, low air pressure in the upper atmosphere, and as a result, air should be moving upward. Given that these two forces, gravitational force and buoyancy force, are at an equilibrium, there is, as of now, no reason for an air parcel to rise or sink. However, that changes when the density of the air parcel changes. If you have an air parcel that has a higher density than its surrounding air, then it will sink towards the Earth's surface. If the density of the air parcel is lower than the surrounding air, then it will rise. But what determines the density of air? The answer is simple. It's the temperature. Lower temperature, higher density. Higher temperature, lower density. So an air parcel that is warmer than its surrounding will rise. An air parcel that is colder than its surrounding will sink.